today we're going to be talking about K and Q. So remember that K is the equilibrium constant. So when the rate of the forward reaction is equal to the rate of the backward reaction, we are at equilibrium. So we have a ratio of product to reactant. And at equilibrium, that ratio equals K. Well, if we take a look at the reaction at any point in time, we can find what's called the reaction quotient, which is Q. It is set up mathematically just like K. The difference is that the concentrations don't necessarily have to be equilibrium concentrations. In fact, if they're not, we will be able to tell that the reaction is not at equilibrium because we're going to compare these two numbers. So always K has to be equilibrium concentration. But Q is the concentration at any given point in time. So if K is more than Q, so let's say K is 2 and Q is only 1. So we know that the reaction is not at equilibrium, but the reaction wants to go towards equilibrium. So would we have to increase our product or reactants to get this number higher? Well, we would have to increase products because products are at the top of the reaction, of the equation. So reactants have to shift to products to make K equal Q. All right, well, let's say that now our Q is equal to K. Well, that tells you something else. If they're equal, it's at equilibrium, so no shifting required. The last one is if Q is larger than K. Well, if Q is larger than K, the only way to bring this number down is instead of increasing products, we have to increase reactants because they're at the bottom of the fraction. So the products have to shift to make reactants. So this would be, the top one is a shift right, and the bottom is a shift left. So let's take a look at two examples. First example, here's our reaction right here. We are given the equilibrium constant, so that is our K that we're going to have to compare our Q to. And then the Q is any concentration at a certain point in time. So these are the concentrations for our Q. We're going to write our Q expression. It looks exactly like our K, so make sure you put the concentration of product over the concentration of reactants to the power of their coefficients. Now I give you moles. Moles is not concentration, but look, liters is 1, so that makes your math easy. So let's plug in for Q. So we have 0.1 squared divided by 2 times 5. When you plug that in, you get 0.001. So that is your Q. Well, let's compare it to our K. Our K is 0.0900, and our Q is 0.001. Which one is larger? K. So that means that we have to increase the reaction quotient to get to equilibrium. So looking back at our equation right here, that means we have to increase the amount of our product. So that's going to make us shift right. All right, here's another one. Same reaction, so same equation for Q, but this time we have different concentrations. The liters is 2, so we must change our moles to molarity. So divide that by 2. All right, so we now have our molarities that we can plug into our Q equation. So we're going to do this. that you get for Q, this time you actually get 0.090, which is the same as our K. So whenever K equals Q, you're at equilibrium. No shift required. Okay, that's it. Have a good day.